Pre-Calc 11, Chapter 6.5. This time we're going to look at the cosine law, and we're going to look at the derivation for it as well. And we use the cosine line for side angle side or side side side. You might have noticed that the derivation for the sine law was rather simple. However, to use it, you have to be careful because of the ASS case. The derivation for cosine is not quite so simple. However, there are no ambiguous cases, so it makes it easier to use. Okay, again, we need to draw the height, h, and this is a right angle. And for sake of simplicity, we'll call this point D. So what we have is c squared equals h squared plus db squared. So this is a right triangle. So c squared, and h in this case means height, not hypotenuse, and we have db squared. So that's fairly simple. We also have the property where h equals b sine c, and h equals b sine c. Okay, so we're just using, in this case, we're considering SOHCAHTOA rather than circumference. So we have opposite over hypotenuse, and that's sine. Now, CD, this side, equals B cos C. And DB equals A minus CD. So DB, the length of this side, is this whole length minus this length. Therefore, dB is also equal to A minus B cos C. We're simply substituting this in for CD. Now let's substitute back into this formula. C squared equals, and we're substituting this in, B sine C squared plus A minus B cos C all squared. C squared equals, now we expand. Okay, this one's easy to expand. We just square both terms. And we put the squared after the sine, meaning we're squaring the value of sine C. If we put the squared after the C, that means we're actually squaring the angle. So you have to get used to this notation. Now we square this, plus A squared. Since this is squaring a binomial, we have to double this value, minus 2AB cos C. Sorry, this is a big C. And plus, now we square the final term, B squared cos squared C. And what we want to do at this point is rearrange. I'm going to put the A squared first, and then I'm going to have B squared sine squared C plus B squared cos squared C, and minus 2AB cos C. Now, we can factor out a B. So we have A squared plus B squared sine squared C plus cos squared C minus 2AB cos C. This is an identity, and it's equal to 1. So A squared plus B squared minus 2AB cos C. So this is C squared. Okay, this looks like the Pythagorean theorem with an extra term. And because we can solve for the triangle arbitrarily, You can also do a squared equals b squared plus c squared minus 2bc cos a. And similarly for b squared. Okay, and as I said before, there's no ambiguous cases for the cosine law. However, it is a little bit lengthier and a little bit harder to remember than sine law. Now, if we look at, say, the angle A here, if this is 90 degrees, cos of 90 degrees is 0. So this whole term becomes 0, and we have the regular Pythagorean formula. Now, like I said, the sine law is easier to use than the cosine law. And the strategy is to use the cosine law once, and then you can use the sine law for the remaining unknowns. Okay, let's look at an example. We have this triangle, so we have side, angle, side. So we need to figure out this side. And notice that we can't use the sine law here, because we don't have the angle for this side, we don't have the angle for this side, and we don't have the side measure for this angle. So a squared equals b squared plus c squared minus 2bc cos a. And we substitute. A squared equals 12 squared plus 16 squared minus 2 times 12 times 16 cos 57 degrees. Now we can plug that all into the calculator, or you can take it step by step. If you want to do step by step, this is 144 plus 256 minus, and we're going to have to approximate that on the calculator, 2 times 12 times 16 times cos 57. That's 209.14, and that is approximately 144 plus 256 minus 209.14. That's 190.86. And that's a squared, so we need to take the square root. And that's 13.8. 13.8 meters. Now we can go ahead and use the sine law. Sine b over 12 equals sine 57 over 13.8. So b equals the inverse sine of 12 over 13.8 sine 57. And that is approximately 46.8 degrees, so we'll just call it 47 degrees. And do we need to use the sine law again here? No, we have two angles, so it's best to just use property of the triangle. That's 180 degrees minus 57 degrees minus 47 degrees. So that is approximately 180 minus 57 minus 47, 76 degrees. Note, you cannot rely on the triangle to be exact measurements. It's not a scaled drawing. Okay, let's look at another example. This time we have side, side, side. So we need to find one angle to get started. So a squared equals, you can choose any one you want, it doesn't matter, plus c squared minus 2bc cos a. So 12 squared equals 13 squared plus 11 squared minus 2 times 13 times 11 cos A. This time we have to do some algebra. It's not just a matter of plugging it in. So first of all, let's move this over to the other side. So we have 12 squared minus 13 squared minus 11 squared equals minus 2, 13, 11 cos A. Cos A equals, we can expand this, 144 minus 169 minus 121. And we're dividing this by this value, minus 2, 13, 11. So angle A equals inverse cos 144 minus 169 minus 121 all over minus 2 times 13 times 11. And we can plug that in our calculator without any intermediate values, so we don't get any rounding errors. Inverse cos, bracket. Because there are terms, we need brackets, otherwise it won't evaluate it properly. Brackets around the numerator, divided by negative 2. And these are all in the bottom, so we need divides. Otherwise, we need brackets around the denominators if we're going to use multiply. 13 divided by 11. And we get 59 degrees. So we're calculating A, that's 59 degrees. Now we don't have to use the cosine law anymore because it's a fairly lengthy process. Let's use the sine law. And we want to find an angle. So let's put sine in the numerator. So sine B equals 13 over 12 sine 59. So B equals the inverse sine of 13 over 12 sine 59. And that's going to be approximately inverse sine 13 divided by 12 times sine 59. And we get 68 degrees. And finally, we can calculate C using the 180 degree property. And that's 61 degrees. So a valid question here would be, do we need to check the ambiguous case? And the answer is no, because all these angles are acute. If this was an obtuse angle, if this angle was obtuse, then we would have to adjust for a quadrant 2 sine value. But we don't have that case here. We can easily see if we have an obtuse case by looking at these sides. If one side was a lot longer than the other two sides, then we would have an obtuse angle case. So, to solve some other applications, we need to understand what the definition of bearing is. It doesn't match angles in standard position. And north is defined to be 0 degrees. And we go clockwise. So east is 90 degrees. And south is 180 degrees, and west is 270 degrees. So here's an application. Find the distance between two ships. One ship spots an airplane at a bearing of 80 degrees and an elevation of 7 degrees. The other ship spots the plane with a bearing of 300 degrees and an elevation of 11 degrees. The airplane reports its altitude as 10,000 meters, and report your answer in kilometers. So, step 1, let's calculate a distance. And we'll do the distance from S1 to the airplane, ship 1 to the airplane, and we'll call this D1. So, this is a tangent operation. The tangent of 7 degrees equals the altitude over D1. We don't want to use the sine function because that would give us the distance to the airplane in a straight line. We want the horizontal distance, so we use tangent. D1 equals 10 kilometers divided by tangent of 7 degrees. So D1 moves up here, tangent moves down there. And this is an approximate value. 10 divided by tan 7. And we get 81.4 kilometers. Let's calculate the other distance between S2 and the airplane. So tan 11 degrees equals the altitude divided by D2. Therefore, D2 equals 10 divided by tan 11. And that is approximately 51.4 kilometers. Okay, so let's label some of this. This is 81.4. This is 51.4. You can see that this is not to scale. And we need to find the distance between the two ships. So we're looking for, this is D1, D2, and we're looking for D3. We need to know this angle. So the angle equals, okay, so this is 300 degrees, and this is 80 degrees. Okay, so this is the angle to the airplane, and this is the angle to the airplane. However, we need the angle going the opposite way. So we have to add 180 degrees to this, so this is 260 degrees, and we have to subtract 180 degrees from this to get the angle going this way. So this is actually 120 degrees. So our angle is 260 degrees minus 120 degrees. That gives us 140 degrees between the two. So now we can go ahead and use our formula for cosine law. D3 squared equals D1 squared plus D2 squared minus 2D1 D2 cos 140 degrees. Substituting our values in, we have 81.4 squared plus 51.4 squared minus 2 times 81.4, 51.4 cos 140 degrees. And that is approximately and cos 140. That gives us 15,678. And the square root is approximately 125 kilometers. And that completes this lesson.